see how that works and if it's going to work. Okay, continue, share screen. Let me see, one participant can share advanced sharing options. Okay, no, that's good. Let me just try to find the button on this to actually share my screen. Speaker view, no, galley view. I see a button that says share screen, but that doesn't let me share. Oh, here we go. All right, let's try to share that screen right there and share. So at this point, you should be seeing a screen that says black body radiation. Let's see. So the interesting thing is, while I'm looking at that, let me see if I can also see, I see the chat, participants. I want to see if I can see you guys as well. No, I can't. So let me put it this way. If you can see the screen that says black body radiation, can you type in the chat?
Yes, we can see it.
All right, well, let's get started then. Because I don't have my setup so that I can't see your faces, but that's okay. I think you're supposed to see me and not me see you. So this is a talk that I have given many times in preparation to give it at this year's AG. Unfortunately, we didn't have the AG. And so it's traditionally a 90-minute talk that starts with radiation and then kind of flows into Einstein's theory of special relativity. And since we don't actually have the full 90 minutes, I'm actually going to kind of start in medias res. Let's see, we see the PowerPoint app, but not the slideshow. Well, let me try this. Let me see, click on slideshow. That should be, let's see. So Thomas is saying, yes, that must mean that you can see something that is good. My screen looks funny, but if you think it looks good, we're going to go with that. All right, so we're going to start in medias res. We're going to start with the very last slide about radiation, and then we're going to flow into Einstein's theories. In fact, the year 1905 specifically. The concept of black body radiation, when you hear the word black body radiation, that's really an imaginary thing. It's an imaginary object that can absorb all radiation, all light, all gamma rays, all X-rays, all any kind of radiation whatsoever. And when the scientists back in the early 1900s were imagining this box, they realized that there's no way you could have a device that absorbs everything without eventually giving back that radiation, because if it kept absorbing this radiation, if it kept absorbing the energy, then eventually it would have infinite energy in it, because it would absorb all the energy in the universe. So what they found out is that all baryonic matter, and when I say baryonic matter, I mean you, me, table, chair, stars, comets, everything in the universe that you can see, feel, touch, taste is what we call baryonic matter. All baryonic matter gives off radiation unless it is at 0 degrees Kelvin, unless it is as cold as is theoretically possible in the universe. And since almost nothing, well, nothing is 0 degrees Kelvin in the universe, everything gives off radiation. So this is going to be important a little bit later when we're talking about Einstein. Oh, the other interesting thing is the radiation that it gives off, the frequency of it, is really based on the temperature of the object. So our sun, which is right around 5,000 degrees Kelvin, it gives off radiation in the visible kind of yellow light spectrum. Whereas you and I, since our bodies are about 300 degrees Kelvin, we give off radiation in the infrared spectrum. So that's why you have those infrared cameras that can spot human beings' temperatures with their head being bright red because it's hot and their bodies being cold and that sort of stuff. That's all because of the temperature of body. Our bodies are actually emitting this radiation in the form of infrared light. So with that said, let's go talk about 1905, which was Einstein's, what they call the Annus Mirabilis, his miracle year. Einstein was a clerk in the patent office, in Swiss patent office, and he would, after work, he would hang out with his friends and he would talk about physics, and they would write letters to each other and things. And in the year 1905, he published 4 scientific papers. And quite honestly, any one of those 4 papers could have earned him a Nobel Prize. As it turns out, only one did, and we'll get to that in a little bit later. But the first of those 4 papers was about Brownian motion. We're not going to spend a lot of time on this one. It basically, there was a physicist who was discussing, before Einstein came along, he was discussing the motion of pollen in water, and it looked very random, and he was trying to describe it scientifically. Well, Einstein came along, and he was able to demonstrate that the motion, this Brownian motion, which worked in either gas or fluids, was not random. It wasn't just bouncing around. It was because there was something smaller there, something that hadn't yet been discovered, which he thought was probably molecules. And it turns out that the atom and the molecule had not been discovered yet. So Einstein's paper on Brownian motion was kind of the foundation for discovering that everything in the universe is made of atoms and molecules. Oh wait, I have questions. I'm going to go ahead and give this a try, because normally with my talks, they're very interactive. You know, the audience is sitting right there. They ask me questions. I go back. Little tougher in this, but I'm going to give it a shot. And if it doesn't work, then I'll wait until the Q&A session. Let's see. Richard asked, does that mean something at 0K will have infinite energy? No, something at 0K, 0 degrees Kelvin, will have no energy. In essence, energy is motion of atoms. So if you're at 0 degrees K, the atoms and the molecules are not moving at all, so they have no energy. And then we got to imagine a black hole is not at 0K, but would give off radiation. Is that radiation cannot escape? Okay, so the question is about radiation coming from a black hole, but we're not going to get into that, because then we're talking Hawking radiation. And that is an entirely strange, weird, wonderful topic that I could spend half an hour just on the radiation coming from a black hole. So Thomas, I'm going to skip your question unless we happen to get to the end and we have lots of time. Okay. The second paper that Einstein did was on the photoelectric effect. It was generally known that there was this thing called the photoelectric effect, which is if you have a piece of metal and you shine light on it, the light will cause the metal to eject an electron. It will create electricity. Or if you had a wire that went around, it would actually cause the electron to flow around. But it's not all light for all metal. Some metals behave differently under different colored lights. And for example, potassium, if you were to shine red light on potassium, which something in the 700 nanometer frequency range, that red light would just bounce off. Nothing would happen. No matter how bright that red light was, even if you had like super, super bright red light, it would all just bounce off the potassium. Now, if you were to shine something more in the green light, like a 550 nanometer wavelength, that light would actually cause electrons to be kicked out of the metal. And if you went to the blue range in the 400 nanometers, that would actually cause a lot of electrons. And the electrons would shoot out quite energetically, and you wouldn't even need a very bright light at all. It could be a very, very dim blue light, but it would still cause these electrons to shoot out. And what Einstein was able to prove with this was that it all had to do with the quantum state of the matter and the quantum state of these photons of energy. Whereas when they were properly aligned, when they were synchronized properly, then you would get the photoelectric effect. So essentially, Einstein explained the cause of the photoelectric effect, which of course now we have, we use it for all of our solar panels and all that other stuff. A question, let's see, I'm going to skip the black. Would a black body object be 0K? No, a black body object would actually be, depending upon how much energy it is absorbing, it would be extremely high energy, because remember, this black body absorbs all energy, and energy and heat are basically the same thing. So the more energy you absorb, the hotter you are. Okay. So that's 2 papers. Now let's go to the third paper, which was Einstein's paper on mass energy equivalence. Now, this is where we have to go back to that black body. You remember I said that all baryonic matter in the universe gives off energy, even if it's as long as it's not 0K, as long as it's not as cold as it could possibly get in the universe, it gives off energy. Well, that idea bothered Einstein because he thought, okay, if I have an object and it is giving off energy, but not absorbing energy, it must be losing something. There must be, you can't just give off energy and not lose something. And so he basically was trying to figure out, does the inertia of a body impact its energy content? And so what he figured out is that when something gives off energy, it actually loses mass. It becomes less massive, which kind of is another way of saying it weighs less. And in fact, what he said was, very specifically, if a body gives off the energy in the form of radiation, its mass diminishes by the energy divided by the speed of light squared. In his formula, L was energy and V was the speed of light. Okay? Now, we probably know that today as E equals mc squared. In other words, the amount of energy that you're giving off is equal to the mass that you are losing times the speed of light squared. And in just a second, we're going to kind of look and see some of the crazy things that happen with this basic principle of physics that Einstein proved. Oh, one interesting fact, going back to the photoelectric effect. Einstein only won one Nobel Prize in his life, and it was for the photoelectric effect. Well, the photoelectric effect and other advances in science. Whereas he probably should have gotten 4 or 5. The other thing you have to remember was it was a very political time, World War II. Einstein was originally a German scientist, but he was a pacifist. He hated pretty much all government. So that was the only Nobel Prize he won, was for the photoelectric effect. So from this, the work that Planck had done in black body radiation, Einstein was looking at this and came up with his famous formula, E equals mc squared. So that's 3 papers. We're going to talk about his 4th paper, but before we do, we have to get 2 science terms out of the way. The first is what we call an inertial frame of reference, because Einstein's theory of special relativity only applies to an inertial frame of reference, which is a frame of reference that describes time in a homogeneous and isotropically independent manner. So I'm going to give you an example. I want you to look at the floor of your room that you're in. And if I ask you the question, is the floor moving? You're probably going to tell me no. Okay? I hope you would. Well, this is Mensa. There's always going to be one person who's trying to be a smart aleck. But okay, so if you told me that your floor is not moving, I would say you are correct. But what if there was an astronaut who was outside of the Earth's atmosphere and was looking down at the Earth, and they could see you, and they could see your house or your apartment or your office, wherever you're sitting, and they're looking at you sitting on the Earth, and the Earth is spinning. So they would say, well, that floor is in fact moving within my inertial frame of reference, because I'm looking down and I'm seeing that Earth spin at 180,000 kilometers a second or something like that. Very, very fast, obviously. So you're saying the floor is not moving, and you are correct within your inertial frame of reference. This other astronaut is saying the floor is moving at the speed at which the Earth is spinning. Now imagine a third astronaut that is outside of our solar system. Okay? So they're not only seeing the Earth spinning around, they are also seeing the sun, or the Earth, revolve around the sun. Okay? So they're saying that it's spinning, but they're saying it's spinning much faster than that astronaut who's just outside the Earth's atmosphere looking at it. Now imagine that there is another astronaut that is outside of our solar system, or our galaxy. And they're looking down at our solar system on one long branch of the Milky Way, and they're actually seeing our entire solar system moving at almost 500,000 miles an hour. Okay? So within their inertial frame of reference, they would say that your floor is moving at 500,000 miles an hour. And the simple fact in physics is they are all correct. There is no place in the universe that is the center of the universe. There is no place in the universe that is not moving. everything in the universe is moving. The universe itself is moving. The universe is expanding at faster than the speed of light. So there is no fixed point that you could ever say that is the single point of reference. So what you have to do in any physics is say, okay, I am going to describe a frame of reference, and then within that frame of reference, any physics statement that I have must be true, but it also must be explainable within some other frame of reference. So that's the science term, inertial frame of reference. The other one we have to talk about is the speed of light in a vacuum. Whenever we mention speed of light, we generally mean in a vacuum, but the reality is there is no place in the universe that is a perfect vacuum, where there is absolutely no matter whatsoever. So the most accurate measurement that we have so far for the speed of light is about 299,000 meters per second. Okay, so for the sake of this discussion, I'm just going to call it 3,000 kilometers per second, roughly. Kind of an interesting fact, the actual first good measurement of the speed of light was done by a Dutch astronomist named Römer back in, I think it was 1630, sometime back around the times of Galileo Galilei. And the way that he measured the speed of light was the planet Jupiter has a moon called Io that goes around it. So when Io is between Jupiter and the Earth, it blocks the light from Jupiter. And then when Io is on the backside, we can see Jupiter, but we can't see Io. So in essence, this Io moving in front of Jupiter and behind Jupiter is like a flashlight, it's like a beacon, because it does it on a steady pattern. But when Römer, I just love saying that name, Römer, when he was looking at it, he noticed that at certain times of the year, it would blink faster than other times. So he's trying to think what would cause this. Is it actually, was it possible that this moon would spin faster sometimes a year than other times? And so what he figured out was that sometime of the year, the Earth is moving towards Jupiter. And so the light from Jupiter and Io is coming at us faster and gets it to us sooner. And sometimes the Earth is moving away from Jupiter. And so it takes light longer to reach us. So he was actually able to estimate the speed, and he was about 75% correct. So remember, there's no computers, no calculators. He's just got like a very basic telescope and rudimentary at that. And from that, he was able to approximate the speed of light in a vacuum. So I love that story. Okay, so now we're going to get to Einstein's fourth paper from 1905, which had to do with what we now call special relativity. And he was talking about the electrodynamics of moving bodies within an inertial frame of reference. Okay, so this is basically saying that the frame of reference that you're in is still. It is not moving. There's another theory that he has, which is his theory of general relativity, that has to do with moving frames of reference. And he made a very basic and simple theory. His first theory is that the laws of physics are invariant in all inertial frames of reference. Now, what's interesting is the person who invented this was, oh, dang it, I think it was Galileo. Yeah, it must have been Galileo. The theory of special relativity and relative motion was actually invented again back in the 1600s. And the examples that Galileo gave, he actually wrote a book on it, had to do with ships and how when you're in a ship, you can't really tell if you're moving because you're in the ocean and that sort of thing. So the first thing, the first part of Einstein's theory of special relativity, which is the laws of physics are invariant, had already been proven by Galileo and pretty much every physicist since then. So that was not a controversial topic. That was not controversial at all. That was generally accepted physics, okay? Oh, by the way, there was a question that says, how is the universe expanding faster than the speed of light? That's a great question for the end. So remind me to answer that question because it's a wonderful question. Okay? The second part of it also seems quite intuitive. The speed of light in a vacuum is the same for all observers, regardless of the motion of the light source of the observer. So what that means is that if I'm sitting still, which again, there's no such thing as sitting still, we are all moving everywhere in the universe. If I'm sitting still and I look at and measure, you turn a flashlight on and measure the speed of that light, somebody who is over there and moving this way will measure the speed of light the same as I do. That seems to make sense. The speed of light is the speed of light. It always moves at the speed of light. But what we're going to see in just a minute is that is absolutely insane. So within this theory of special relativity, Einstein basically proved that both of these are true. Now, for that to be true, certain really crazy things have to happen. And so that's what we're going to talk about now. Now, let's take a step back to the third paper that he wrote, which is where he came up with E equals mc squared. Okay, obviously, you know, one of the things, the outcomes of E equals mc squared is that the atom bomb, you know, nuclear bombs, because you can take a very small amount of mass. You know, a modern atom bomb uses like about this much plutonium, like a handful of plutonium. I mean, it's, you know, and the destruction that it can generate is greater than the original atom bomb, which was, you know, the size of a room practically. So there is a, you know, a small amount of matter has a lot of energy in it. So that's kind of, we understand that now because we grew up in the atomic age. But there's some things you might not realize about that. For example, if I had two watches, and let's say that these watches were identical in every single way, down to the atom, just they were identical. They were not wound, though. They were both just sitting there, and their little dials are not moving. If I put them on a scale and I weighed them, they would weigh the same because their masses would be identical. But if I took one of them and I wound it up, when I wind up the watch, I am adding potential energy because the spring is winding. And then when I stop winding it and it begins to tick, that potential energy is converted into kinetic energy because you're getting the motion of the dials and the gears. And the gears, as they turn against each other, are causing friction, and that becomes heat energy. And so there's all kinds of energy inside the watch that I wound up that is not inside the watch that is not wound up. So now, after winding one of the watches up, if I weighed both of the watches, the one that I wound up would actually weigh more because it would have a greater mass. A little bit weird, a lot of bit weird, in fact, but it is a simple outcome of Einstein's proof that energy is equal to mass times the speed of light squared. Okay. So the next thing that is weird is we talk about the speed of light in a vacuum being the same for all observers. So I would like to give you an example. I think that's the next slide. Yes, I want to give you first an example within Galilean relativity, which is not weird. You're going to find it very normal. The second example I'm going to give you is within special relativity, and that's where things are going to get a bit weird. Okay. So within this first example, I want you to imagine that there is a train moving on a straight track, perfectly level at 100 miles per hour. And inside the train is Bob, our buddy Bob, and he has a flashlight in his hand. But he cannot see outside of the train. So since the train is moving at a constant speed of 100 miles an hour, and he can't see outside the train, Bob doesn't know that he is moving. He has no reference outside of the walls of his train. And he looks at his flashlight and he goes to turn it on and it doesn't work. And Bob is angry. So Bob throws the flashlight in the direction of where the train is traveling, and he throws the flashlight at a speed of 25 miles an hour because we can measure everything magically. Okay. So if I go to Bob and I say, Bob, how fast are you going? Bob would say, I'm not moving at all, because he has no reference points. He can't see anything outside that happens to be going past him at 100 miles an hour. And if I asked Bob how fast the flashlight was going, he would say, well, it's 25 miles an hour. I threw it in that direction, and it is traveling at 25 miles an hour. And Bob would be correct. Within his inertial frame of reference, Bob is correct. Now, oh, Bob. So, yeah, okay, so here's the next part of that example is imagine that there's a train station. Let me see if that, how did that slide? Okay. Imagine there's a train station and Mary is sitting on the train station and sees the train go by right as Bob is throwing the flashlight. Now, for some reason, Mary can see inside the train. I don't know why, but it's a made-up story anyway. So Mary can see the train traveling at 100 miles an hour. She can see Bob inside going 100 miles an hour. And she can see the flashlight moving away from Bob in the direction of the train at 25 miles an hour. So if I were to ask Mary, how fast is the flashlight moving? She would say that the flashlight is moving at 125 miles per hour, the speed of Bob plus the speed that the flashlight is moving away from Bob. And she would be right within her inertial frame of reference. So Bob says the flashlight's going 25 miles an hour. Mary says it's going 125, but it's very easy to understand. It's very logical. That's because Bob doesn't know that he's going 100 miles an hour, and Mary sees Bob going 100 miles an hour, so that's why she has a faster. Now let's get into special relativity. Kind of the same example, but this time Bob is in a rocket, and that rocket is traveling at 200,000 kilometers per second, which is roughly 2/3 the speed of light. Okay? And he's got this flashlight, and this time the flashlight works. So he points the flashlight in the direction that his rocket is traveling, and he turns the switch on, and he has a device that can measure the speed of the light coming out of his flashlight. Now, do you remember earlier where Einstein said the speed of light is the same for no matter what your inertial frame of reference is? And that is 300,000 kilometers per second. So if I ask Bob how fast he's moving in the rocket, he's going to say, I'm not moving at all, because he doesn't, again, he's got nothing outside to see. He's locked in this thing. So, and he's moving at a constant speed. So he has no way of knowing that he's moving, but he does measure the light as it moves away from him. And as he's measuring this light, he's measuring it at the speed of light, because light always travels at the speed of light. So he said the photons of light that are coming out of a flashlight are moving at 300,000 kilometers per second. Okay? That should make sense to you. But now let's go to Mary, because Mary happens to be sitting in a rocket ship station, if there is such a thing, or will be such a thing, and she's watching Bob go by. So I say to Mary, how fast is Bob going? And she says, well, Bob is inside of a rocket ship. The rocket ship is traveling at 200,000 kilometers per second. So Bob is traveling at 200,000 kilometers per second. And then I say to Mary, how fast is the light coming out of the flashlight, in the direction that Bob is traveling? And you remember Einstein, the speed of light is the same regardless of your inertial frame of reference. So Mary's going to say, the light is traveling at 300,000 kilometers per second away from Bob. So there's a problem there, because if I ask Mary how fast the light traveled, and she says that the light is traveling at the speed of light, and Bob is going at 200,000 kilometers per second, go back there. Shouldn't Mary say that the light is traveling at 500,000 kilometers per second? Because it's Bob's speed of 200 plus the light speed of 300. But it isn't. According to Mary, the light, when she measures the light is traveling at 300,000 kilometers per second. According to Bob, who's moving in the same direction as light, he also sees the light traveling at 300,000 kilometers per second. How is that possible? It defies our normal sense of logic. There are two reasons that are kind of after effects of Einstein's theory of special relativity. One is time dilation, and the other is length contraction. So now let's talk about those two elements. I think, there we go, time dilation, length contraction. Okay? With time dilation, what that basically means is the faster you go, and the closer you are traveling to the speed of light, the slower your clocks run, such that if you ever actually reach the speed of light, your clocks would essentially not move at all. Time would not move for you. So if you think about it, when you look at a star, and that star is 5 billion light years away, according to our clocks, that light has been traveling for 5 billion light years. According to that light, that photon of light, it hasn't taken any time at all. It it got from where it was to where we are in an instant because the light was traveling at the speed of light. So here is an example. If you look at the chart of time dilation, basically what you're seeing is that, you have to go really, 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 really close to the speed of light before you start experiencing this time dilation. If you were to look at the fastest man-made object in the world, the chart that you see there, where you see time dilation of like 1, which is what we are right now. We are traveling at what is 1. I'm going to be talking about the Lorentz factor and how that 1 is calculated. But if right now we are traveling at 1, the fastest man-made object in the entire history of man, which is a space probe, it's not Voyager, but it was another probe. I can't remember the name of it right now, but it is traveling at roughly 400 or 400,000 miles per hour. Yeah. So if you look at that, if you were to calculate it using the Lorentz formula, and we'll talk about the Lorentz formula in a second, that would be a 1.000024, I think. So the fastest object, man-made object in the history of the universe is still at that very, very low time dilation speed. So it is experiencing almost no time dilation. But even then, we've done time dilation experiments. We've done things where we've taken 2 atomic nuclear clocks perfectly synchronized, sent one up in an airplane and had it fly around the Earth. And then when it landed, it was actually slower than the one that had been sitting on Earth because its speed had increased and its time had slowed down. So, okay. So now let's talk about length contraction, because the faster you go, the closer you get to the speed of light, the shorter distance becomes, but only in the direction that you're traveling. So if you go, if you start going really, really fast, close to the speed of light, it's not like everything shrinks, but everything in front of you shrinks as you measure it. So for example, let's say you were to drive a car, you were to rent a car, and you know what? I don't have my notes in front of me for this. So I'm going to do this by memory. I hope I get it right. If I get it wrong, please don't call me out. So if you rent a car in New York and you drive it to Los Angeles, okay, and it's a brand new car and the odometer says 0 miles per hour. When you get to Los Angeles and you look at the odometer, it will say 5,000 miles, assuming you travel in basically a straight line. Okay, so that distance would seem normal to you because everything, the US is 5,000 miles apart, and you're driving 5,000 miles. So if you took another car in New York and you drove across country at 80% of the speed of light, when you got to Los Angeles, your odometer would say that you traveled 2,500 miles per hour. It would actually say that you traveled a shorter distance. And in fact, you did travel a shorter distance, because the closer you get to the speed of light, length contracts. The distance you travel is shorter. And that's the reason that Bob and Mary could both see light traveling at 300,000 kilometers per second. The reason is because Bob was measuring a kilometer that is shorter than Mary's, because the direction that he's traveling, length is contracting, and also time is contracting as well. So when he's measuring how far did it go and how long did it take it to get that distance, he has different length and different time from somebody who is not traveling at that same speed and is looking at it from a different inertial frame of reference. And there's my picture of 2,500 miles per hour. So here are some other crazy examples of length contraction. Let us say there's a train on a train track, and there's a mountain, and the mountain is exactly 1 kilometer wide. Okay? And there's a tunnel that goes right through it, but the train is 2 kilometers long. So as you might expect, the train will begin to enter, and you won't be able to see the beginning part of the train until it gets to the very other side of the mountain. And then as it starts to come out, the back end of the train will disappear inside the mountain. Okay? So, but you will always either be able to see 1 kilometer of the back of the train, or 1 kilometer of the front, or 1 kilometer of some part of the train, because the train is 2 kilometers and the mountain, that tunnel, is 1 kilometer. But if that same train was traveling at 80% of the speed of light, then the actual train would fit inside that same tunnel, and you would not see either end of the train. It would actually pass through the tunnel. You would see the train as basically a 1 kilometer train, even though the person on the train would think that they got on a 2 kilometer train if they measured it before they left. Okay? Oh, there we go. Another strange part that comes out of this, the theory of relativity, is event simultaneity. Simultaneity. I always get that one wrong. Okay. So with event simultaneity, these frames of reference become very, very important. If I go to a baseball game, assuming that I would be allowed to, non-COVID times, and I would be watching, and I would see a pitcher throw a ball, and then I would see a batter swing the bat and hit the ball, and then I would see the ball go over the outfield fence for a home run. Those events happen in the same order, no matter where I sit in the ballpark. In fact, no matter where I am in the universe, as long as I am within the same possible frame of reference. But there are other places in the universe where my frame of reference no longer applies, because I am moving so fast and I am in a different relative frame that I would not see those events happen the same. It is possible that the light from the events that I'm seeing would hit somebody who's way out in outer space, traveling at near the speed of light in a direction this way, a direction opposite of me. It is possible that they would see the ball go over the fence, then they would see the pitcher throwing the ball, then they would see the batter hit the ball. They don't need to see the events in the same order that I see them if they're in a different frame of reference. If they're in a frame of reference that is so different that they would experience the light differently. So that's kind of one of the science fiction theories of time travel, in that I can go back in time because I can go fast enough or in an arc enough or some other way that I can see the last thing happen before the first thing happened. So I would be essentially traveling backwards in time just because I was in a different frame of reference. Okay. Oh, and Thomas says the mountain isn't moving. That's correct. The mountain did not move in the previous example, at least in terms of the person watching it. Okay. So one of the things you may hear is we talk about, can we go faster than the speed of light? What is interesting is it's not really kind of the speed of light, is the speed of causality. It was what I was talking about this just a second ago, with the fact that light is it's how we experience the light, and within our frame of reference we can't do that. One of the things you hear a lot of times is that at the speed of light, mass becomes infinite. That is not true. Okay, that is based upon a way that physics has always been taught, that takes out one of the critical factors of the physics that we do. And let me explain what that is. Okay, that is wrong. Bum, bum, bum. It is really inertia that becomes infinite. So what happens is, as you get closer to the speed of light, you need more and more energy, more and more power to push you faster. And so the formulas that you would use to calculate that, to prove it, would show you that at some point before you reach the speed of light, you would need an infinite amount of energy in order to achieve the actual speed of light. So let me explain kind of why. This is where I was talking about, alluding earlier to the Lorentz factor. When we teach momentum in physics, junior high school physics, we say, the momentum is equal to mass times velocity. Okay, and that's true. That is an accurate thing to say. I'm wondering, is my sun feels like shining on my face. So I'm going to try to play with it because I can't see myself in this darn setup that I have here. I hope that's still working. Okay. So you can ping me in chat if I'm like out of frame or something like that. So we say momentum is equal to mass times velocity, and that's a very simple thing, and it is correct and it is true, but it's not completely true. It ignores the special relativity that Einstein. It works great at slow speeds, but it doesn't work good at all as you start to approach the speed of light. The true thing is that your momentum is equal to the Lorentz factor times mass times velocity. And in fact, if you remember correctly earlier, where was that slide? There. Okay. So the slide, this chart basically shows you the calculation of the Lorentz factor. So that red line, which is very flat along the 1, that means your Lorentz factor is 1. And at 10% of the speed of light, your Lorentz factor is still pretty darn close to 1. And 20% of the speed of light, your Lorentz factor is still pretty darn close to 1. 30% is starting to climb up a little bit. Okay. So that is the Lorentz factor. So when we are calculating momentum, we need to actually calculate in the Lorentz factor. Now, Henri Lorentz was a very good friend of Albert Einstein. They worked together. They wrote each other all the time. The interesting thing was when Lorentz came up with this Lorentz factor, he was trying to prove an ancient Greek theory about the ether, about the fact that that everything in the universe is in something called an ether, which is some unseen force or matter or something that we're floating in. And he was trying to calculate why it was harder to go faster through water than it was, through air. And so he came up with this Lorentz factor, which seemed to be universally applicable. And as it turned out, it was universally applicable within Einstein's theory of special relativity. But unfortunately, Lorentz was kind of crazy with this ether thing. Although now that we're learning about dark energy and dark matter, which we're not going to talk about in this thing, it is very possible that Lorentz was right. It's possible that, in fact, we do exist in this ether of dark energy and dark matter that we can't see, touch, feel, taste, or anything. But nonetheless, it's there, and it affects our entire notion of space and time. But that's not what we're talking about today. So what happens in these physics courses is instead of teaching about the Lorentz factor, what they do is they come up and they have this thing they call relativistic motion, or relativistic mass. And so when you hear people say that your mass becomes infinite as you approach the speed of light, what they're really saying is this: it's relativistic mass, but there's really no such thing as relativistic mass. It's a way of teaching matter. The correct way is to include the Lorentz formula in it. And so if anybody asks why you can't go to the speed of light, tell them it's because you need infinite energy to make you go that fast, instead of saying that your mass becomes, because your mass doesn't actually change. You don't become like really big and have a giant head and like you're a monster, you're going to do things if you go faster. It doesn't work that way. Never has. Okay, so that's it. We are at the question and answer section. I am actually going to try to minimize my screen so I can see you wonderful people. No, I'm not going to do that. Let me try this. I'm going to stop sharing. Well, I'm going to leave this up. Let me see if I can do this. Because if you look on the screen, you'll see the link, the bit.ly. That's the actual presentation. If you want a copy of it, it's available to. Oh, wait, you're recording this, so people can go back and watch the recording. So I don't need to leave this. I can actually.
Yeah, why don't you stop screen sharing so we can see everybody?
Stop share. There we go. Ooh, yeah, that light's terrible. I'm glad I'm over here.
Yeah, you got some serious sunlight going on there.
I do. I got to figure that out. I got to put some screen or something. Anyway, so questions and answers. What do you got for me?
That was deep, Timmy.
Yeah, I tried to, I tried to keep it. It's a little bit tougher when you can't stop me in the middle of something and say, what about this? What about that? because when it's interactive, I can slow it down and do stuff like that. So I know that we're online. I don't want to keep people too
Well,
long.
there were a lot of questions that you did stop and answer. That was
Yep.
great.
Yeah, I like that. It kind of worked nice with that chat window on the side.
Okay.
Stanley.
What always, can I say
Oh.
something, or should I raise my hand on the thing? Oh,
I-
hi.
think-
When I was somewhere in grade school, we saw this video or movie on relativity, and it was, they showed twin brothers. One stayed on Earth and the other one went into space at the speed of light. And when he came back, he was still the same age he was when he left, but the other one had aged. And that never made any sense to me.
Well,
So how could that possibly be? Didn't he exist as long as his twin who stayed on Earth?
so here's the funny thing about that. That thing that you heard is very, very common. In fact, if I went back to my slide deck, I have a hidden slide that I didn't show you because I could spend pretty much half an hour just on that. It's known as the twin paradox. Okay, and it's very common. It's a very common physics stuff. If you Google twin paradox, if you go to YouTube and you type in twin paradox, you're going to find 1,000 explanations for it. And quite honestly, half of them are wrong, completely and totally wrong. They're not even physicists at all. They don't know what they're talking about. But here's the thing. The key word is paradox. Okay, because the reason that it's a paradox, if you remember earlier where I said there is no point in the universe that is considered the center. There is no point in the universe that is still. So everything in the universe is moving. So if the classic story is, if I hold an apple and I let it go, most people would say the apple falls down to the ground. That's correct. But you could also say that the ground falls up to the apple and everything on earth is falling up. Those two statements are perfectly valid, since there is no place in the universe that you could say, this is the center, this is fixed. I know this is my reference point for everything. There isn't. Everything is moving. So you could pick any frame of reference that you want and say, this is what is not moving and everything else is moving. It's funny because if you think pre-Copernicus, the original Earth-centric models of the universe, where the sun was revolving around the Earth and all the other planets were. That is, technically, it's correct. Yes, we could say the Earth isn't moving and everything in the universe is moving around it. Now, realistically, no, because the models are a lot simpler if you say that the Earth is going around the sun than it is to say the sun is going around the Earth. So the reason they call that a paradox is because they say, all right, well, if the guy who went away and came back is younger, why can't you say that he wasn't moving and the guy on Earth moved away from him and came back? That's where the paradox comes in, because you could say either way. And the reality is, the way that the statement is worded, that the person who left went close to the speed of light, like 80%, 70%, depends on which version you're looking at. What happens is, because you've defined the problem that way, that he was the one that was moving close to the speed of light, then it's just simple mathematics, and it is in fact correct. And just like I said, when I was talking about time dilation, what happens is his clock is moving slower as he goes faster, as he approaches the speed of light. Okay? So, and when I say his clock, I don't just mean his watch, the thing on his wrist. I mean his entire world. His heart beats slower. His brain thinks slower. Everything, if he was to pour water out, the water would pour more slowly than a person that's not traveling close to the speed of light. And the interesting thing is, it's not only that he is younger when he gets back, but also he hasn't traveled as far as, so if that star that he traveled to was 10 light years away, when he measured how far he traveled, he would say, oh, I only traveled 5 light years because that length contraction. And that's basically the simple explanation is that. If you want the real explanation, you need to get into the mathematics of special relativity. And I couldn't even begin to explain that to you.
Okay, next question is Stanley. Oh,
Let me unmute myself.
Okay.
Yeah, I actually have two things I find hard to understand. One is dark matter and dark energy, and the other is the equivalence of time and space.
Mhm.
Maybe you could talk about those two.
Absolutely. So dark matter and dark energy are actually really simple, right? Once we started to getting a really good detailed understanding of how the world works with quantum physics and how matter works together, there was a very simple realization that we had two problems. The first problem is the way that galaxies like ours, our Milky Way galaxy, the way that they spin and the way that they hold together matter, there's, by the rules that we have, there isn't enough matter to hold it together. In other words, we should, all of these galaxies, I'm going to go like, all of these galaxies that are spinning in a big spiral, they should fly apart. They should be, there's not enough matter there and for the gravity to hold them together and keep them spinning. So the entire universe, these planets should just be flying, but they're not. They have these galaxies that are these nice circles. And even our solar system with the sun and the planets that are going around, there's not enough matter in the sun and the planets to keep that going. So there must be some other kind of matter there that is holding this together, and that's dark matter. And the reason we call it dark matter is because we don't know what it is. We can't measure it, we can't see it, we can't find it, but we know that if there wasn't something there, that everything, all of these things that loop around each other and spin in circles, they would just fly off. Now, the second part of the problem has to do with the expansion of the universe. Okay, the universe is expanding faster than the speed of light. Oh, that was a question. Remind me to get back to that one in a second. Okay, so based upon what we know about all of the matter in the universe and how much energy it currently has and how much it pushes out, there is no way that the energy in the universe is enough to keep the universe expanding at that current rate. And so the only way that we can make the mathematics work is if we come up with this thing that we call dark energy. And with dark energy, that's the missing formula. And the interesting thing about dark matter and dark energy is once we apply the formulas, the calculations are almost the same everywhere. There's another problem that in physics where, depending upon how you do the math, you get completely different numbers. But fundamentally speaking, there must be dark matter to hold the planets together, and there must be dark energy to keep the universe expanding that fast. Okay? So you had, what was the second question, Stan?
The equivalence of time and space.
Okay, so this kind of, the way that Einstein's theory of relativity came to be was really quite simple. It's that, if you measure light, no matter who's looking at it, everyone's going to measure it the same, and that's actually been proven. You can, you shoot a beam of light and you measure it by 10 different people. One's moving, one's not moving very fast, and they all measure the light at the exact same speed. Okay, so that's kind of where we came up with we kind of backed into that whole thing of, well, if the light isn't changing, then our observation of it must be changing. And so that's how the faster you go through space, the slower you go through time, and vice versa. The slower you go through space, the faster you go through time, because they are inexorably linked, as Einstein proved in his theory of relativity. So they are no longer two separate things. Isaac Newton was certain they were two separate things. They had nothing to do with each other. But Einstein proved that no, they are linked. You can't go through one without affecting your travels in the other. Interesting fact, in a black hole, that gets flipped. In a black hole, you can go move forward and backwards in time, but you can only move in one direction in space. You always move, no matter which direction you move, you're always going to the exact same place, which is toward the singularity. Okay.
You have a question? Ed
Les.
raised his hand.
Oh,
Ed
okay.
Wojciak? Ed?
Yes, this is Ed's wife, Alice. We're both listening. Thank you. Hi. So what I wanted to know is the twin paradox. You did explain it and said that it was true. But my question is, how can I believe it?
You can't. Well, no, you can. You can go take physics courses. And you can basically become a quantum physicist or an astrophysicist. And in that case, it's pretty simple. You just plug the numbers in and it works. But again, it's the way the problem is worded. When you say this person is moving at 80%, at that point it's just a math. It's just, you just plug in the numbers in the math. I will say, if you're interested in that topic or pretty much anything I ever talk about, there's a YouTube series by Dr. Don Lincoln from Fermilab here in Illinois. And he does a great job of explaining these really complex things very simply.
Okay, but I wasn't asking for the mathematics or how I can
Yep.
drive it. I wanted to believe it. Do you believe it?
I do. So the most simple reason I believe it is because the experiment that was done where they took two nuclear clocks and they left one on Earth and they put one in an airplane and flew it around the globe, and they came back and the clocks were different. And not only were the clocks different, but they were different exactly as the mathematics predicted they would be. So when you have something like that that says, oh, the mathematics says that this guy is moving and his clock is different, and then you test it and it works, and that's not the only experiment. It's the experiment is so simple now that master students in physics can do their own experience with lasers, shooting them up to the moon and back and measuring the time and things like that.
Okay, thank you.
Okay, Richard, next question.
Yes. Hi. Okay. So I apologize for the baby in the frame, but I had a question, a misunderstanding. For me, when I see a jet at an air show go by at the speed of sounds or faster than the speed of sounds, I see the jet and then I hear the jets.
Mm-hmm.
And for my question is, with the speed of light and Einstein's inertial frame of reference, if something is going 90% the speed of light, if it goes past me, then do I see it later, or do I never see it at all, but it still passes me nonetheless because of the time or the distance? I don't remember what the word you used, but the distance dilation and whatnot.
Yep.
With the train going through, the 2 kilometer train going through the 1 kilometer mountain.
Right.
If there's no mountain in the way, do you still see the train go by at the speed of light, or does it just no longer exist because of the difference in the inertial frame of reference?
No, because everyone experiences the speed of light the same, everyone will see that light. It doesn't matter how fast or slow you're going compared to that light. So if this rocket ship shoots past you and it's going almost the speed of light, you're still going to see it. The question is what is it going to look like? Because the appearance of it is going to be different to you versus the person who's sitting on the plane. So to you, who's basically not moving, and again, we're saying not moving. There's no such thing as not moving, but that's what we're saying. To you who is not moving, when it goes by, you are going to see it go by. You are going to see the lights from, assuming it has some kind of light shining on it that you could actually see. So you are still going to see it, and you're going to measure that speed of light at the same thing. But if you measure how fast it's going compared to that person measuring how fast they are going, you guys are going to have completely different measurements because you're going to experience.
Fair enough. And the next question is, since they're moving so fast, as you approach the speed of light, do you start seeing in front of you darkness, or do you see?
No, as you approach the speed of light, if you were in a rocket ship, traveling at the speed of light, what happens is you still see light. Everything looks the same to you, okay? Because your space is contracting. So time is contracting and space is contracting. So even though you are going in your frame of reference incredibly slow, your clock is ticking. So you could travel, again, the example is the light, but there's a star, I can't remember the name of it. The Hubble telescope measured it in 2016. It is 10 billion light years away or something like that. So the light we think it traveled this amazing distance, like all the way across the galaxy, because the galaxy is 14 billion years old. This is 10 billion. So it had to have traveled at least more than halfway across the galaxy. If you were to be that photon of light that travels from that star, you would say, oh, I've only gone about that far, and it's taken me about a second to get there. Because that's it, because you're going so fast, your time and your length would be contracted so much. It would still be normal to you. You would still, think everything's fine and okie dokie. You wouldn't realize it, that other people would say, wow, you're going really fast and you're traveling really far.
So according to every photon in the universe, the Big Bang happened instantly ago.
According to every photon, because photons are electromagnetic radiation, they all travel at the speed of light. So yes, according to every photon in the universe that originated in the Big Bang, it happened less than a second ago.
Okay, next question. Parisa,
Sorry.
and then after that, I believe is Elisa and Thomas.
Les is going like this too. Don't forget Les.
Okay,
He's waving his
he
hand.
raised his hand, so I'm.
No, he's just doing that.
He did it literally. Okay.
Yeah.
Parisa, and then we'll go to Les.
All right, thank you so much for
Well,
the.
why not me?
I didn't see you raise your hand.
Yeah, my hand is up.
Who's speaking? I don't see.
Me.
Alyssa.
Oh yes,
I've been on here a while.
yeah. Parisa raised it before you.
I just had a question about the train and the mountain again. So before you got to that part, you showed the map of the United States and said, like, I think you said if we were flying and you went so fast, it wouldn't show that you went this distance. It would show that you traveled less
Basically.
distance.
Yep.
So, but the actual vessel that you're traveling in, that didn't change. So that's kind of where I got confused. Like the train is the vessel. So in the other one, it was like, it felt like the space that you traveled shrunk on the map. So then I was thinking the mountain would shrink, not the vessel.
Yeah. So I totally understand that. Let me give you a different example, because you're right. The picture that I showed of the mountain was from somebody outside looking, but in fact, they would still see the train at 2 kilometers. Let me give you a different example that might be a little bit easier. Let's say there's a barn, okay? And the barn is 100 feet. And it has doors at either side. Okay. Now I'm on a stick that's 200 feet, twice as long as the barn is. Okay. So if I was going slow, if I was walking with this stick, I would get in the barn, and if the door on the other end was closed, I would run into that while the other side of my stick is sticking way out of the back of the barn. Okay. So now let's pretend I am traveling at 90% of the speed of light, super, super, super fast, okay? Even though my stick is twice as long as the barn, my stick is 200 yards and the barn is 100 yards. Let's say a yard, okay, that's a big, 100 yards, that's a big barn. Oh well. Anyway, 100 somethings, 100 units, okay? And my stick is 200 units, twice as long as the barn. If I'm going 90% of the speed of light, if this barn door is closed, I can come with my stick and I can fit my entire stick in the barn. And they can close this barn door. And so my entire 200 unit stick is in the barn. And then they can open this barn door and I can get out without ever touching the barn doors. The stick was twice as long as the barn, but from my frame of reference, because I was traveling so fast, distances are compressed. And so I can fit through something that somebody on the outside would say, no, because it is too big. In fact, somebody on the outside would not see me compressed that way because they're not going my same speed. I know it's a tough one.
Thank you so much.
It's a lot easier with the math, but then the math is impossible. So
Thank you.
Okay, Alyssa.
Okay, my question came to my mind about 20 minutes ago, but I still think I'd like to hear what Timmy has to say. When you were talking about dark energy and dark matter, you were saying that this is the term that you give to that area in between bits of energy or bits of matter. So why isn't it called unmatter?
well, you got to be careful.
Instead of, how did they come up with the term dark energy rather than unmatter or unenergy or non-energy to
Well-
kind of give you an idea that it's related.
Couple things. You got to be very careful about the term unenergy or non-energy, because it's really close to antimatter, you know, and antiprotons and anti-energy, which are really things. They really exist, and they are completely different from anything having to do with dark energy or dark matter. I didn't name it, but I'm pretty sure the reason they called it dark is because you can't see it. There's no way that we can possibly detect it. We don't have any
Why not?
visibly,
Why not invisible then?
you know, probably because dark is easier to say than visible. I don't know. Again, there is absolutely no way that we even have imagined that we can detect it. Even our greatest tool, the CERN super collider, there's just nobody's come up with an idea that said, hey, if we do this experiment, maybe we can detect dark energy or dark matter. We just don't know. We know that it's there. We just don't know how we're going to find it.
Okay, thank you.
Okay. Next is Les.
Yay, Les. I hope it's a good question.
I have a question and a comment. The comment is they actually did the twins theory and everything with the twins, the one on the space station and the one on the ground. And they've been able to measure the difference because they went around so many times. My question is, do you believe that there will ever be a general unified theory?
Yes, I'm working on it right now. Of course, I know nothing about science. I'm just kind of making this stuff up. So, so yes, I believe that our theories will continue to advance the way they have advanced in the past, because they are constantly advancing. I mean, there's always somebody coming up with a new idea, new way to measure, new theory, you know, and with obviously the biggest discovery recently, you know, in my time is the Higgs boson, which was this strange, weird thing that nobody thought it might exist, and then all of a sudden, boom, you know, we actually prove that it exists, and that advanced theory. You know, the biggest question mark right now is gravity, because we have this quantum theory of everything, but we don't have a theory of gravity. Gravity doesn't fit into it, and gravity's tough because gravity is so small that you can't. It's hard to measure it, because whatever you're doing, whatever instrument you're using to measure gravity is affecting gravity. It has mass. Anything with mass has it. So. But do I think we're going to get there? Yes. In my lifetime, no, not at all. But we keep getting better every year.
Thank you. Hey, Stanley. You have your hand up?
I already asked my questions.
Oh, okay.
Yeah.
You lower your
Okay.
hand. Okay. All right. I have in the chat, so maybe I misunderstood
Yep.
neutrinos.
Neutrinos.
Neutrinos. But if they move close to the speed of light, do they have near infinite energy? That's from Thomas.
Okay. So a couple things about neutrinos. Right now, your body, every inch of your body is being blasted with 600,000 neutrinos every second. So these neutrinos, most of them coming from the sun, are just shooting through your body, and almost every single one of them shoots through your body, and you don't even know it. It doesn't touch anything, doesn't interact with you at all. In fact, they go through the earth, and they don't even interact with the earth. There's these high energy particles that just blast through everything. Okay. Are they moving at the speed of light? Oh God, I wish that's a question I really should know. I'm going to say yes, because they're fundamental particles. They are not electromagnetic radiation. It'd be easier if they were electromagnetic radiation, because then the answer is yes. So, gosh, I wish I had the answer. I don't actually know their speed, but they're certainly moving close to near the speed of light. Just because you brought up neutrinos, kind of a couple fun facts. The neutrinos detectors, there are a lot of people trying to find neutrinos, just detect them. And the way that we do it right now is there are three main places. In Japan, there's a giant pool underground, like way underground, filled with hundreds of thousands of gallons of water, like billions of pounds of water. And they have these photo detectors all around it. And if a neutrino hits a piece of water, it gives off light. because it's very rare that they actually interact with matter. But if they hit it, then there's kind of this kind of the Cherenkov radiation that comes out of it, and so they can actually detect it. Another way they do it is in Antarctica. There's 2 experiments. One is they have the photo detectors in the ice, and so they look for that. And the other ones, they have the detectors on balloons up above the ice. And again, the same thing. They're looking for neutrinos that come through the Earth, like all the way through the Earth, and then they get to Antarctica and they hit the ice, and they react with it, and they show off, they throw off particles that can be detected. We can't detect the neutrinos. We can detect the particles that they hit after they hit some matter, and they throw stuff off.
Okay, I have another question. I don't know if it's tongue in cheek, but so does that explain how they get all that stuff in a TARDIS inside a police call box?
Well, you see, the TARDIS is pretty simple physics. It's just larger on the inside.
Okay. All right, I'm not seeing any other raised hands. Anybody else have any questions?
Parisa does.
Teresa.
I have a couple more if we have time. Some are fast.
I've got all the time in the world. It's you guys that.
2 of them are fast. One's probably got an explanation. In the beginning, you introduced matter, and you said, like, I think you called it bariatric matter.
Baryonic, yeah.
Baryonic. So is there another kind of matter that's non-baryonic?
Yes. So basically, you've got everything comes down to 2 types of matters. To simplify it, because I'm trying to remember the other name, baryonic, but the other are bosons. So with baryonic matter, what we're made of, basically it's the reason that we have structure and form, and our electrons hold themselves together, and we can't walk through walls and stuff like that. The other type, oh my God, I wish I could remember what it is. Anyway, like bosons, you've heard of Higgs bosons. Bosons are non-baryonic. So if I had a glass of bosons and another glass, and they were 100% full, both glasses, and I poured this glass into that glass, nothing would overflow. And I could take another glass and pour it in another glass, another glass. They share their space. They have no worries about being in the same spot, about having the same quantum state as each other. So these bosons and the non-baryonic matter, again, it's killing me that I can't remember. But anyway, so there are basically other types of matter in the universe, and especially dark energy. Dark energy and dark matter make up 95% of the universe. The baryonic matter, the things that we can see and touch and feel, are only 5%.
Oh, okay, perfect. Thank you. Second question, the 2 clocks, and you said if you wind 1 clock, the mass would increase?
Yes.
So if you put one outside in the sun, would the same thing happen?
Absolutely. Okay. Any type of energy you want, potential, kinetic, heat energy, friction energy, anytime you add energy to something. Take the case of 2 watches. If I lift one watch up higher than the other, it has greater potential energy, because if I let them both go, this one's going to fall with more energy than that one. So if I take 2 watches and I lift one up, this one has more mass just by doing this, just by lifting it up, it has more mass.
Okay, great, and thank you. And the last question is a little more involved. The flashlight, when he's in the train and the conductor's throwing the flashlight, I wasn't sure if I was imagining it. Did they throw the flashlight outside the train or within the train car? It didn't matter.
Within the car, because the part of it is he can't see outside. So he's standing in the back and he throws it forward. Eventually it's going to hit the front wall pretty quick. 25 miles an hour, it's going to hit the front wall in about 1/10 of a second. But nonetheless, the idea is he can't see outside, but he's throwing it toward the front of the train.
Okay. If he threw it outside of the train, what would happen? It's totally different, right?
No, it's basically the same thing. The problem is if he throws it outside the train, then can he see it? If he can see it, then he can look outside, and then he's going to know, hey, wait a minute, I'm on a train and I'm going 100 miles an hour. So that changes his frame of reference. He now thinks he's now on an Earth that isn't moving, but he now thinks he's going 100 miles an hour because he can see the ground outside.
Okay, I was thinking, like, when you first said it and you first asked us, I was like, well, if he throws it outside and he's not throwing it faster than the 100, it would like come backwards. But I don't know if I wasn't thinking.
Yeah, no, because the train is actually traveling at 100. By the way, if you're interested in frames of reference, there's a really great video on YouTube It was done by MIT. I can't remember the name of it. But it's about frames of reference. It was done in 1950s. I mean, it's a black and white old, with the announcer over it. But it's really cool. They did a great job of it, the way they photograph different frames of reference. And you're looking at something and all of a sudden you realize, oh, wait a minute, that isn't the thing I'm looking at because the camera's moving with the object. So highly recommend that.
Thank you so much.
My pleasure.
Hey, Dan raised his hand. You're muted.
No, can't hear you.
Okay. All right. I didn't get it. Okay. Since you say how things are all relative, there's no one frame of reference, and you at one point kind of alluded to the problem that you can't really say for sure that it's the spaceship that's moving and not Earth or vice versa. But that seems to make a problem for some of these examples, like the train going through a barn or past a mountain or whatever. From the point of view of the people in the train, I think it's the mountain and the barn that are getting shorter, but for the people outside, it's the train that's getting shorter, or is it the other way around? I can never get it straight. But whatever it is, it seems like if the train fits in the barn in one frame of reference, it wouldn't fit in the frame in the other one because it's the barn that got shorter instead of the train, right?
Right. So the answer to that is actually Galileo answered that exact question in his theory of special relativity back in the 1600s. Because what he said, and it's still true today, it says if you come up with a physics formula, some calculation, that calculation has to be true and accurate, no matter how you are observing the experiment. So what Galileo said, if I'm on a ship and the ship is sailing this way and I drop a ball, I see the ball, I can measure the distance of the ball, but somebody outside the ship sees it differently. But we can both calculate what the other person saw. That's the secret. It's like, it doesn't matter how I experience it. If I can calculate how somebody else would have experienced in their frame of reference, and that formula that I have is accurate in both frames, then it must be a good formula. If it's not accurate, then it isn't.
The person standing on the dock would see the ball go at a diagonal, I think.
Yes, that's exactly it. But as long as they can explain why they saw it at a diagonal and the other person saw it as dropping straight down, and they can do that with a mathematical formula, then that formula must be inherently correct in physics.
So does the train fit in the barn or not?
Yeah, yes, no. It depends. Depends on your inertial frame of reference. But you could, but the secret, especially when you're trying to explain the twins paradox, is that you have to be able to calculate the other person's frame of reference. You have to explain it, because there's a really fun video explaining what happens if the two people are on video camera, the person on Earth and the twin that's in the spaceship, but they watch each other on video camera like constantly, because now, wait a minute, how can this guy be younger if they're both watching each other on this video camera? But then it gets really weird and complex, because then you're talking about the speed, because the video signals are traveling at the speed of light and he's moving away at 80% of the speed of light, and it gets really insane, but it's fun.
All right. I think we had one more hand. Richard. You had a question?
Muted? Yes. Okay. My question went back to the Einstein special relativity with the inertial frame of reference, where I think it was Copernicus, you said, was observing Io.
No, that was Orle.
The
Danish guy.
The Danish guy. Yeah,
The Danish guy with Io. Yeah.
So my question was, he saw that the Io was blinking faster as Earth was approaching Jupiter, as Earth was approaching Io.
Mm-hmm.
But you said that the speed of light is equal despite the inertial frame of reference. And I was just hoping you could help me understand why the light was blinking faster as he was approaching it, with a different inertial frame of reference versus the Earth going away from Io.
So actually, the easiest answer, and there's some very complex answers to that. The easiest answer has to do with the Lorentz factor. Remember where I said that the fastest object in the the universe that we've launched is 400,000 miles per hour, and its Lorentz factor is 1.000000024 something. So the actual, assuming that there were two different frames of reference, one where he was moving toward it and one where he was moving away. If you want to make that assumption, then you can say the actual difference in speed was so minuscule that you can't even measure it. And that's kind of why he was 75% close. I mean, there's a lot of other major reasons, but even if he had all the stuff, the best measuring stuff in the world, he would have been off by the Lorentz factor. But that, again, it's so small, so incredibly small that it would not have made any difference.
And the Lorentz factor is the spatial, not the time dilation.
No, it's space and time, but think of it as a multiplier. Okay, the closer you get to the speed of light, the larger it becomes, and the more dramatic these time and space effects come. Remember, length contraction.
Graph.
Pardon?
That exponential graph.
That exponential graph. So you saw that you have to be going at least 40 to 50% before you start to notice, like personally or seriously notice these length contractions and time dilations. It is possible. Like I said, we've measured it on Earth, and we're not going. Our Lorentz factor is pretty much 1, and even the fastest thing we do is 1.00000. So it's not like there's, you got to go mind-bogglingly fast, but nonetheless, you think of that Lorentz factor as the multiplier that causes all these effects.
Would the Lorentz factor be the Earth speed approaching plus the Io speed approaching as well? Would it be the sum of those speeds?
No, because see, now we're getting back into the whole which is moving. Maybe we're not moving at all. Maybe they're coming back and forth between us. Really, the reality is there's another factor here that's hard to describe and hard to get your head around, which is there is an actual speed of light. Any photon in the universe, any X-ray, gamma ray, microwave, they all move at the speed of light. They're all moving, and that's a fixed thing. That's the speed of light. That's it. Nothing goes faster than the speed of light. So we are moving at a speed. We have no way of knowing what that speed is. We might be moving at 80% the speed of light. Probably not. But there's no way to know. The only way we can measure our speed is relative to something else, and if that thing is moving, then there's no way.
So the only way to accurately measure the speed of light would be to include a fourth dimension.
Interesting thought. Hadn't thought about it that way, but yeah, realistically, the easiest way to measure the speed of light is to go the speed of light and then look at everything else, because everything else, if you're going the speed of light, then everything else is either going the same speed as you or some different speed.
Well, no, because then again, if you're going the speed of light, are you going fast, or is someone else going is something else stationary, or are you?
No, if you're going the speed of light, you're going fast. But again, time is stopped for you, and distance is nothing. So everything else looks super fast because time is stopped. Your watch is not ticking, basically. So when you look at something else, you say, "Wow, that thing's going really fast," even though you're the one that's going fast. So you kind of have. Not only do you have to go to the speed of light, but you have to know that you're going the speed of light. And that's the way, there's no way to tell if you're going the speed of light or not.
So distance or speed is rate over time. And if there's no time, then there's no rate.
And there's no way to measure rate. Because rate has distance, and you can't measure distance.
Yeah.
All righty. I don't see any more hands raised, but I do have a question. Timmy.
Yes.
What is your day job?
I work in a bank.
Bank?
This is purely my hobby. This is just a hobby for me.
Wow.
I just spend all day with this. I just love this stuff. I love it.
I have to tell you, you brought me maybe 25% closer to really understanding this. It's a difficult concept to wrap your mind around.
It is.
You did a fantastic job.
Thank you.
Providing some illustrations, some analogies, and concepts that helps me, a non-scientist, wrap my head around this whole theory. And I think I'm probably speaking for some other people on this call. I see a hand raised there. I love the mountain. The mountain was fantastic. I love the watch.
Yep.
It really helped a lot. I appreciate that. And I appreciate you taking the time to spend with us and share your knowledge.
That was my pleasure.
You're a banker and you're.
I'm a bank guy. I work in a bank. Yep. And by the way, if you guys want any more of these, I've got a million topics. I mean, this is only half of the talk of the AG. I didn't even do the radiation. I love the radiation. The radiation one's exciting. That's fun. Wow. So you guys want me back anytime, just let me know. Happy to do it.
We will certainly dive deep into that because we want to do this at least once a month. We have weekly cocktail hour on Zoom, but once a month we want to have some kind of subject like this that everybody can educate themselves with. And this was fantastic.
Cool.
I greatly appreciate your participation. And Leslie, I think you're the one that brought them to the table, right?
Yes, I saw it and I thought it would be great for our group. So thank you so much, Timmy. And I'm an ex-banker too, so.
You have my sympathy.
Yeah, I got out. I was smart. I left.
Yep.
Okay, well, I don't see any other questions raised, and it has been 2 hours or more. Yep. And so I think we should close this meeting. I'm still recording. I'm going to save this recording and provide it to Leslie to post it on the.
Oh, wait.
Is Les? I think Les is going like this.
Right.
He's either having a heart attack or he wants to talk.
Les, go for it.
He's muted.
You're muted. All right, I'm going to unmute you.
I was trying to unmute.
Wait, I unmuted you. Oh, now he muted it. I crossed him. He muted himself after I unmuted him.
There we go. He's live. Go, Les. You're good.
Just a personal question, Timmy. Did you try to enter the field?
No. You know what? Long story short, I absolutely loved it. But then all of a sudden, people kept offering me jobs in banking and finance, and I was CPA, and so I just kind of went for the money instead of what I love. So, but now I'm old and I get to do what I love in my free time.
Thank you so much, Timmy. Another question from me. I'm going to allow you an opportunity to plug yourself because you said you were running for the top next year.
Yes. So the election is a long way away, and I'm going to be running for chairman. And so at some point in December, sometime, I'm going to be issuing basically a position statement on why I'm running and what I think we need to do. So if I could ask a favor, when I issue that paper, if you could go ahead and just read it and see if you like what you read, because I think we need to get some things done, and I think I can do it.
Excellent.
Thank you, Timmy, for
based on
presentation.
I agree.
Okay.
And as they applaud on Zoom, I'm clapping to you. Thank you so much for your presentation.
Thank you.
Thank you, Timmy.
Really,
all right.
Bye,
everybody.
That came.
Hi, Timmy.
All right.
Hi, Ann. Hi, Ann. Good to see you again.
Teresa, welcome to our group.
Thank you for having me. It was so cool. Very fun.
It's great having you. Yay.
Thank you guys so much. I liked it.
We look forward to your involvement in the group.
I'll be in touch with you, Cindy.
Okay. You good.
Thank you.
Bye, everybody. Bye.
Bye-bye.
Bye, everybody.
God, end.